Welcome back to The Explainer. You've heard of GPT, right? Well, today we're pulling back the curtain on the one piece of tech that makes it all possible, the attention mechanism. Seriously, this is the secret sauce. It's how these models actually understand what we're saying.
All right, so to really get this, let's look at something that used to be a huge headache for AI, language translation. Take this German sentence. If you just go word for word, you get this mess, right? It's total nonsense. To get it right, you have to shuffle words around, get the grammar, understand the vibe of the whole sentence. And that, right there, shows you just how tough context is for a machine.
So attention is the hero of our story. But every hero story needs a problem to solve. And to appreciate the solution, we got to look at how things were done before and, well, why it just didn't work. It all boils down to this thing called the long-distance problem. Okay, so the old-school approach involves something called a recurrent neural network, or RNN for short. The idea was pretty intuitive, actually. It tried to act like us, reading a sentence one word after another in sequence, hoping to build up meaning along the way. Simple idea, right? But here's the fatal flaw. Imagine reading a whole book and then having to summarize the entire plot on a single tiny sticky note. That's basically what the RNN had to do. It would read the whole sentence and then squeeze all of its meaning into this one little memory cell called a hidden state. And then, from just that one sticky note, it was supposed to write out a perfect translation. Yeah, not going to happen.
You can see the problem, right? It's a huge information bottleneck. If you have a long, complicated sentence, the stuff at the beginning, poof, it's just gone by the time the model gets to the end. The crucial context gets completely washed out. The model literally just forgets the beginning of the sentence.
So this failure, this bottleneck, it's exactly what sparked the breakthrough. Researchers realized they needed to ditch this one memory cell idea and come up with something way, way more dynamic. And this is where things get really cool.
The question they asked was so simple, but it changed everything. They said, okay, what if we stop forcing the model to remember the whole thing at once? What if, at every single step, we let it look back at the entire original sentence and just pick out the words that matter most right now?
And that, my friends, is the core idea of self-attention. For every word it's looking at, the model gets to ask, how important is every other word in this sentence to me? It does this for all the words, creating these supercharged, context-aware versions of each one. It's like each word suddenly understands its place in the universe of the sentence.
So, how does this magic actually happen? It's basically a three-step recipe. First, it calculates attention scores, just a number that says how much two words are related. Then it does a little math to turn those scores into weights. Think of them like percentages of importance. And finally, it uses those percentages to mix everything together and build that new context-packed word.
Okay, so that basic idea was already a huge leap forward. But the real genius, the thing that lets models like GPT learn and get so powerful, is how they implemented this. They came up with this brilliant analogy based on how a search engine works using three components: queries, keys, and values. Here's how to think about it. Imagine you're in a library. Your query is the question you have in your head. You go around and look at the keys, which are like the titles on the spines of all the books. When you find a title that matches your query, you pull the book off the shelf and get the value, which is the actual content inside. Simple, right? And here's the thing. This isn't just a cute analogy. It's literally what's happening under the hood. The model learns three special sets of instructions, or matrices. For every single word, it creates a unique query, a unique key, and a unique value. And by training these matrices, the model actually learns what connections are important. It learns what to pay attention to. This whole process gets a fancy name, scaled dot product attention. But don't let the name scare you. This formula you're seeing, this is the beating heart of pretty much every modern AI. You multiply the queries and keys to get those relevant scores. You scale it, which is just a little trick to make the training process go smoothly. Then you normalize the scores, and boom, you use those to get your final context-rich output. A single formula powering this entire revolution. It's pretty incredible. Okay, so this all sounds great, but there's a catch, a big one. Remember, we're often using these models to generate text, like writing an email or a story, one word at a time. And to make that a fair test of its intelligence, there's one really, really important rule. No cheating. That's the rule. Think about it. If you're predicting the next word in a sentence and you can already see the next word, well, that's not much of a prediction, is it? The model is only allowed to look at the words it is already written, not the ones that are coming up.
See, by default, this attention mechanism is kind of like a know-it-all. It looks everywhere. Forwards, backwards, all at once. It creates this full grid where every word is connected to every other word, no matter where it is in the sentence.
So to stop it from cheating, we do something that's actually super simple. We apply what's called a causal mask. All this does is block its view of the future. It's like putting blinders on it. For any word it's currently on, it can only see that word and all the words that came before it. No peeking ahead. Problem solved. All right, so we've got one really smart attention mechanism. But here's the final, mind-blowing piece of the puzzle. What if you're trying to understand something complex, and one point of view just isn't enough? Well, you scale it up, and this is where we unlock its true superpower. The big idea was, why stop at one? Instead of one set of query, key, and value matrices, what if we had a bunch of them, like 8 or 12 or even more, all running at the same time, in parallel? Each one could be looking for something totally different. This is what we call multi-head attention, and it's like having a whole committee of experts analyzing a sentence. You've got one head that's a grammar nerd, checking sentence structure. You've got another that's a historian, looking for connections to facts. Maybe another is a poet, tracking the emotional tone. Each one finds different patterns, and when you put all their reports together, you get this incredibly deep, layered understanding of the text.
And this is not just a theory, it's exactly how it works. Look at a real model like GPT-2. The smaller version had a team of 12 of these attention heads. The bigger version had 25. Each one learning its own specialty, its own way of looking at the data.
So let's just quickly pull all that together. We started with the problem. Old RNN models had a terrible memory. The big idea, attention, was to let the model look at everything at once and pick what's important. The engine that makes it all work is that query key value system. Then we added a rule, the causal mask, so it can't cheat by looking into the future. And finally, we gave it a superpower, multi-head attention, letting it process things in parallel from tons of different perspectives.
It's amazing, right? This one elegant idea completely solved that long-distance memory problem. It gave AI a working memory, and that unlocked, well, everything we see today with generative AI. And that leaves us with a huge question. If attention solved the problem of memory, what's the next great barrier? What's the fundamental ability AI needs to unlock to take the next leap?